Welcome to the deep dive. Anyone watching Modern Finance knows that volatility is, well, it's basically the norm now, isn't it?
It really is. And that kind of environment pushes predictive models hard.
Exactly. We're seeing traditional stats models, even some standard machine learning approaches really struggling to keep up. They hit limits with data volume, model complexity.
And crucially, maintaining the kind of precision and computational stability you need for reliable risk prediction. It's a tough balancing act.
You often trade speed for stability or the other way around, right? Especially with all the nonlinearity in financial data.
That's the core problem we're tackling today, this ceiling on robustness.
So what's the potential solution we're digging into?
It's a really fascinating approach, actually. It aims to break through those limits by integrating ideas from pretty different fields: quantum computing principles and bio-inspired optimization.
Quantum and bio-inspired. Okay, that sounds like a mix.
It is. The specific model is called the quantum-inspired chimpanzee optimization algorithm with Kernel Extreme Learning Machine. Bit of a mouthful.
QChOA-KELM for short, I imagine.
QChOA-KELM, yes. It's presented as a novel biohybrid paradigm.
So our mission for this deep dive is basically to dissect this QChOA-KELM framework. Look at the theory, the optimization, the results.
Exactly. We'll go through the mechanics, the optimization strategy, and the empirical results from the source paper. And the results are why we're really talking about it.
What's the headline finding?
A reported 10.3% accuracy improvement over just the baseline KELM model.
10%. That's substantial in this field.
It is. And they report at least 9% superiority across the board accuracy, F1, AUC, compared to a whole suite of conventional methods. Achieving that kind of gain definitely warrants a closer look at the architecture.
All right, let's do it. Where do we start? The KELM part.
Makes sense. Let's start with the foundation.
Yeah.
The Kernel Extreme Learning Machine, KELM. But even before the K, the base is the Extreme Learning Machine, ELM.
Right, ELM. That's the single hidden layer feed-forward network, known mostly for its speed.
Its training speed, absolutely. And that speed comes from a really clever simplification.
Unlike backpropagation, where you're tuning everything.
Exactly. In ELM, the input weights and the hidden layer biases are just randomly initialized. And then they're fixed. They don't get trained.
So the only thing the network actually learns is the output weight vector. Let's call it beta.
Precisely. The learning objective function, fx, is just the hidden layer output, let's say hx times beta, or in matrix form, h times beta equals L, where L is your target output.
So training just boils down to solving that linear system for beta. H beta equals L.
That's it. Since h is fixed, you just need to find beta. Ideally, if h were invertible, beta would just be h inverse times L.
But H is almost never square or invertible in practice.
Almost never. So instead, you use the generalized inverse or the more Penrose pseudo-inverse h star. So beta equals h star times L.
Okay, so that's fast. But you mentioned limitations earlier. Stability, generalization.
Yes, that basic ELM solution can be quite brittle. It can struggle with noise and complexity, which is obviously a big problem in finance. That's where the KELM modification really becomes essential.
This is where the kernel part comes in, along with regularization.
Exactly. KELM brings in two key things for stability and power. First, regularization. It adds a regularization coefficient, C, and the identity matrix, I.
This sounds like ridge regression or support vector machine concepts.
Very similar principle. Instead of just finding any beta that solves H beta L, you're looking for a solution that also minimizes the norm of beta itself. It leads to the minimum norm least square solution.
So you're balancing fitting the data with keeping the weights small and stable.
Precisely. The mathematical form for beta then changes. It becomes beta equals H transpose times the inverse of H transpose plus I over C times L.
Okay, that I over C term, that's the key for stability.
That's the regularization term. It ensures that the matrix we need to invert, H transpose plus I over C, is well conditioned, even if HH transpose on its own isn't. It makes the solution much more robust to noise and helps prevent overfitting.
Got it. So that handles stability. Now, the kernel function, this is the kernel trick.
Yes, the famous kernel trick. We implicitly map the input data into a potentially much higher dimensional feature space without actually having to compute the coordinates in that space.
Leveraging Mercer's theorem, right, to turn nonlinear problems into linear ones in that higher dimension.
Exactly. The crucial insight for KELM is that the matrix product HH transpose, which appears in that regularized solution for beta, well, that product can be directly replaced by a kernel matrix, omega ELM.
where omega ELM is defined by Ka lie xj, the kernel function evaluated for all pairs of input data points.
Precisely. You define the kernel matrix omega ELM as HH transpose, which equals KHAYXJ.
So you substitute that kernel matrix back into the regularized solution.
And you get the final KELM prediction function. Equation 5 in the paper shows it nicely. Fx equals this vector of kernel evaluations between the new input x and all training points times that inverse matrix term times L.
So the prediction for a new point depends only on its kernel similarity to the training points. You've bypassed needing to specify the hidden layer mapping H altogether.
That's the elegance of it.
And the specific kernel used here was the Gaussian kernel.
Yes, the Gaussian radial basis function, RBF kernel. Kx1 by 2 equals e to the power of minus the squared distance between by 1 and by 2 divided by sigma squared.
Okay, a very common choice. Powerful. Maps to infinite dimensions.
But it immediately highlights the two critical hyperparameters we absolutely need to get right for KELM to work well. First, that regularization coefficient, C, we just discussed. It controls the trade-off between fitting the training data and generalizing.
Okay, and the second?
The variance parameter in the Gaussian kernel, sigma squared. The paper often calls it S. This controls the width or influence of each data point.
Right, how smooth the decision boundary is.
Exactly. Finding the optimal combination of C and S is absolutely crucial. And that's the job of the next layer we need to talk about, the optimization engine. The success hinges on finding the best C and S.
Perfect segue. We've got the KELM engine, which needs precise tuning. Now we need the sophisticated fuel for that tuning. The quantum-inspired chimpanzee optimization algorithm, QChOA.
Right. We're shifting gears from the network architecture to the metaheuristic search strategy.
Why not just use something standard like grid search or random search for CNS?
Well, the search space defined by CNS can be surprisingly complex. You can have lots of local optima, places where you think you found the best setting, but there's actually a much better one elsewhere. Standard methods can easily get stuck.
Okay, so we need something better at global exploration, and that's ChOA, chimpanzee optimization.
Yes, QChOA was proposed fairly recently in 2020. It's a bio-inspired algorithm based on group intelligence specifically. It models the social hunting behavior of chimpanzees.
Hunting behavior, how does that translate to optimizing CNS?
The idea is that the way chimpanzees coordinate, driving prey, setting barriers, chasing, represents a very effective search strategy. The algorithm tries to mimic that dynamic to explore the CNS space efficiently, aiming for faster convergence and higher precision than simpler methods.
Interesting analogy. Let's break down how QCOA works. It starts with initializing a population of potential solutions, right? Pairs of C and S values. How does it avoid just starting randomly?
Good question. Random initialization can sometimes cluster the initial search points, biasing the search. To get better diversity right from the start, QCOA uses something called the circle chaotic method.
Chaotic method, not just random.
Right. It uses a chaotic map equation, equation 13 in the paper, to generate the initial population matrix P. The points are pseudo-random, non-repeating, and tend to be more uniformly spread across the search space defined for C and S.
So better initial coverage of the possibilities.
Exactly. That initial diversity is really important for boosting the global search capability later on.
Okay, so the chimpanzees, our CS pairs, are initialized. Then they start hunting for the best solution, driving and chasing prey.
That's the core loop. Each chimpanzee updates its position, its C and S values, based on the location of the prey, which represents the best solution found so far.
How is that update calculated?
It involves calculating a distance d between the chimpanzee's current position, xchimp, and the prey's position, xprey. The formula is d equals the norm of c times xprey minus m times xchimp. Then the position is updated. Xchimp plus 1 equals xprey minus a times d.
Okay, those coefficients AMC, they control the movement.
Yes, they manage the exploration versus exploitation balance. There's another key coefficient, f, which decreases non-linearly from 2 down to 0 over the course of the iterations.
How does F affect things?
When f is high, early on, the a coefficient tends to be larger, allowing for bigger jumps, more exploration. As f decreases towards 0, the jumps get smaller, allowing the chimpanzees to fine-tune their positions around the best-known solution, more exploitation.
That sounds somewhat similar to how coefficients work in particle swarm optimization, for example. What's unique about the QChOA part?
A key difference is the explicit modeling of the social hunting structure. QChOA introduces an attack mode.
Attack mode.
Yeah, it recognizes that in a real hunt, different individuals have different roles. The algorithm designates the 4 best chimpanzees, based on their current fitness, into specific roles: attacker, barrier, chaser, and driver.
Okay, so the 4 leaders, what do they do?
Each of these 4 calculates its own potential next position based on its role and the prey location, using slightly different update rules, equations 18, 19, 20. Let's call these potential positions x1, x2, x3, and x4.
And the rest of the chimpanzees.
Their final updated position for the next iteration isn't based on just one leader, but on the average of those 4 best potential positions. So xt plus 1 for the others is x1 plus x2 plus x3 plus x4, 4.
Ah, I see. So the group moves based on a consensus of the top performers. That encourages convergence towards promising areas.
It does,
Wonderful.
but there's a risk, right? If everyone just follows the leaders, they could all converge on a local optimum and get stuck.
Good point. How does QChOA avoid that?
It introduces a crucial element of randomness or chaos. It models the idea that chimpanzees might simultaneously attack and search for other opportunities. Mathematically, there's a 50% probability, controlled by a parameter mu, that a chimpanzee will follow the normal update rule based on the 4 leaders.
And the other 50%?
The other 50% of the time, it uses a chaotic map, equation 21, to generate a completely random jump, exploring a potentially different part of the search space. This explicit mechanism for breaking away from the consensus is vital for escaping local optima.
Okay, that explains the QChOA part, the bio-inspired hunting strategy. Now, where does the quantum-inspired part come in? That's the Q in QChOA.
Right, this is the enhancement that adds another layer of sophistication and, importantly, a stronger theoretical basis for exploration. The quantum update method doesn't replace the QChOA logic. It refines it.
How does it work? Is it simulating actual quantum bits?
Not actual quantum hardware, no. It's quantum-inspired. It uses the mathematics of quantum mechanics, specifically quantum rotation gates, to modify the chimpanzee's position.
Rotation gates, like in quantum computing algorithms.
Exactly like that. Each chimpanzee state can be represented as a quantum state vector, QT. The update involves applying a rotation matrix, R theta, to this state, Q plus 1 equals R theta QT. This rotation effectively changes the search direction in the parameter space.
And the angle of rotation theta isn't fixed.
No, and this is really clever. The angle theta is dynamically adjusted based on the fitness of the chimpanzee's current solution. It's C and S pair.
How does fitness affect the angle?
The formula is given in equation 24. Theta equals pi 2 times 1 minus fx, where f is the current fitness and phi max is the worst fitness in the population. Remember, we're minimizing error, so a smaller fitness f is better.
So if a chimpanzee has found a really good solution with low error, its f is small.
Which means f max is small and 1 f max is close to 1. So theta is close to pi 2. No, wait. The paper says a smaller fitness results in a smaller rotation angle. Let me recheck that logic. Perhaps phi max represents the best possible fitness in the formulation used, or there's an inversion. The key concept stated is, better fitness leads to small rotation.
Okay, assuming that's the mechanism. Good solution means small rotation. What does that achieve?
It means if you're already near a good solution, low error, the quantum update makes only a small adjustment. It focuses on fine-tuning, on exploitation. But if your solution is poor, high error, high fest relative to facts, the rotation angle is larger, causing a bigger jump, promoting exploration to find a better region.
So the quantum rotation automatically balances exploration and exploitation based on the quality of the current solution.
Precisely. It provides a mathematically grounded way to control the search intensity.
And this quantum component helps with convergence. The paper claims a proof.
Yes, the convergence proof is a significant part of the paper's contribution. They argue that because the objective function values are shown to be monotonically non-increasing with each iteration, and the search space for C and S is bounded, the algorithm is guaranteed to converge.
To a global optimum.
Given the bounded space and assuming a continuous differentiable objective function, which holds reasonably well here, the non-increasing sequence must converge to a limit, F star, which they argue is the global optimal solution. This theoretical guarantee is a big advantage over purely heuristic methods.
That sounds powerful. But adding chaotic maps and quantum rotations must increase the computational cost, surely. What's the complexity?
The paper states the overall time complexity is O, T times, T max times N plus N log N.
Okay, let's break that down. T is the number of iterations.
Yes, the main loop iterations, set to 50 in the experiments. N is the population size and number of chimpanzees, set to 30.
And T max.
That relates to the inner calculations for position updates within each iteration.
What about the N log N term? Where does that come from?
That typically arises from sorting. In each iteration, the algorithm needs to identify the 4 best chimpanzees to designate them as attacker, barrier, chaser, and driver. Finding those top 4 requires sorting, or at least partial sorting of the population based on fitness, which takes n log n time.
So identifying the leaders is actually a key part of the computational cost.
It often is in these kinds of population-based metaheuristics.
Mm.
But given that T and N are fixed and relatively modest, 50 and 30, the overall complexity remains quite manageable, especially compared to the potential benefit of finding a much better solution.
Okay, so we have the KELM network needing CNS and the QChOA designed to find the optimal C and S. How exactly does QChOA know what optimal means? What's the fitness function?
This is critical. The design of the fitness function dictates the entire optimization process. Get it wrong, and you might end up with a model that looks great on paper, but fails in practice.
So what did they use? Just minimize the error on the training data?
No, and this is a really important design choice. They specifically chose not to do that because it leads directly to overfitting.
Right. Optimizing only for training error makes the model memorize the training set but fail on new data.
Exactly. So the fitness function here is defined as the minimization of the sum of the error rate on the training set and the error rate on the test set.
Both, simultaneously.
Yes. Equation 7 shows it. Fitness equals argument of trainer rate plus test error rate.
That's interesting. Usually you use a validation set for tuning, or maybe just monitor test error, but not put it directly in the objective function being minimized by the optimizer.
It's a strategic move. By forcing QChOA to minimize the combined error, the search process inherently has to balance fitting the training data well and generalizing well to the unseen test data right from the very beginning. It penalizes solutions that overfit.
So the prey the chimpanzees are hunting is the C and S pair that gives the lowest combined error across both data sets.
Precisely. The mathematical form, equation 10, just formalizes this. Object at JCS is the average indicator of misclassification on the training set, plus the average indicator of misclassification on the test set. Minimize that sum.
Let's think about the impact of optimizing C and S through this lens. What happens if QChOA finds an optimal C that's very large?
A very large C heavily penalizes misclassifications on the training data. The model is forced to fit the training set almost perfectly, potentially capturing noise. This reduces training error but likely increases test error due to overfitting.
Yet a very small C.
A small C prioritizes minimizing the model's complexity, the norm of the weights. It encourages simpler, smoother decision boundaries, improving generalization and reducing the risk of overfitting. But if C is too small, the model might underfit, failing to capture the true underlying patterns, leading to higher error on both sets.
So QChOA is trying to find that sweet spot for C that minimizes the sum of the errors.
Exactly, the Goldilocks C value.
And what about optimizing S, the Gaussian kernel width, sigma squared? How does that play out with the combined error objective?
S controls the reach or influence of each training point. If QChOA finds an optimal S that's very large.
Large sigma squared means a very wide, gentle Gaussian.
Right. The mapping to the feature space becomes very smooth, potentially blurring the distinctions between classes. The model might become too general, missing subtle but important patterns, leading to higher error because it can't discriminate effectively.
And a very small S, very narrow, peaky Gaussian.
A very small S makes the model highly sensitive to local data structure. Each point has a very limited influence. This can lead to very complex, wiggly decision boundaries that perfectly fit the training data, including noise. Again, low training error, but high test error due to overfitting.
So QChOA, minimizing the combined error, is searching for the S value that creates just the right level of smoothness to separate the classes effectively while still generalizing well.
That's the goal. Finding the optimal balance for both C and S simultaneously is what QChOA is designed to achieve.
Okay, the theory sounds solid, but models live or die by the data they're trained on. This was applied to a Kaggle weekend hackathon dataset for financial risk. How rigorously was the data prepared?
Data prep looks quite thorough in the paper, which is crucial. Financial data is notoriously messy.
Missing values, how are they handled?
They used a hybrid approach. For numerical features missing less than 10% of values, they used median imputation.
Median, not mean.
Median, yeah. Less sensitive to outliers, which are common in finance. For features with more than 10% missing, they used regression imputation, predicting the missing value based on other related features.
Smart. And outliers. Finance has those too. Sometimes they're errors, sometimes they're real extreme events.
They used the IQR method interquartile range. Anything outside Q1 minus 1.5 times IQR or Q3 plus 1.5 times IQR was flagged.
And deleted.
No, importantly, replaced. Replaced with the nearest boundary value, Q1 1.5 IQR, Q3 plus 1.5 IQR. This caps the influence of extreme values without losing the data point entirely. For categorical outliers, they used mode replacement.
Okay, imputed missing values, handled outliers, then feature selection. They went from 42 features down to 18. That's a big
It
reduction.
was a two-stage process. First, a filtering stage.
What did filtering involve?
Two main things. Removing features with very low variance, less than 0.1 because they don't offer much discrimination, and tackling multicollinearity. They calculated Pearson correlations between all feature pairs, and if the absolute value was greater than 0.8, they removed one feature from the pair.
Standard practice to improve model stability and interpretability. What was stage 2?
Stage 2 is a wrapper method. This is more sophisticated. They actually used the Chimpanzee optimization algorithm itself, the basic QChOA, not the quantum version here, to search for the best subset of the remaining features.
How did that work? What was the fitness function for this QoA?
The fitness was the classification accuracy of the KELM model trained using only the feature subset being evaluated by QChOA.
Ah, so it directly optimized the feature set for the specific model being used.
Exactly. It finds the combination of features that yields the highest KELM performance. That's how they got down to the final 18 features, ensuring they kept the most impactful ones like leverage ratios, liquidity metrics, market volatility indicators, etc.
One last critical data issue, class imbalance. Financial risk is usually skewed, lots of low-risk cases, few high-risk ones. How is that addressed?
Yeah, the paper states the ICE under risk target variable was 78% low risk, 22% high risk. That's significantly imbalanced. They tackled it in two ways.
First,
On the training data only, they applied SMOTE synthetic minority oversampling technique.
SMOTI creates artificial minority class samples.
Right, it generates synthetic examples by interpolating between existing nearby minority class neighbors. This helps balance the class distribution in the training set without just duplicating existing rare samples.
Okay, so SMOTI on the training data, what was the second approach?
The second was adjusting class weights within the KELM model during training. They used a formula to assign higher weights to misclassifications of the minority high-risk class. The formula was y equals n times log NA.
So errors on the rare high-risk examples cost the model more during optimization.
Exactly. It forces the QChOA-KELM system to pay much closer attention to correctly identifying the high-risk cases, which are often the ones you care most about predicting accurately.
Okay, meticulous data prep, sophisticated optimization. Let's get to the payoff. The experimental results. They used tenfold cross-validation.
Yes, tenfold CV for robust performance assessment. The setup seems solid. Python 3.8, a decent CPU, i7-10700K, and importantly, a powerful GPU, RTX 3080, which really helps with the matrix mass in KELM.
And the specific QChOA-KELM parameters.
They used 50 iterations, 30 chimpanzees, a quantum bit probability of 0.55. The search ranges for the hyperparameters were C between 1 and 20, and sigma squared S between 0.001 and 1.
And how was the baseline KELM configured for comparison?
The baseline used fixed parameters, C10 and sigma squared 0.01. Kind of standard default values, not optimized. This comparison isolates the benefit gained specifically from the QChOA optimization.
Right, so what were the headline scores? Table 7 and Figure 8 in the paper.
The results for QChOA-KELM were striking mainly for their consistency. It achieved a score of 0.96 across the board.
0.96 for everything. Accuracy.
Accuracy 0.96, balanced accuracy 0.96, ROC AUC 0.96, and F1 score 0.96. Uniformly high performance.
That's impressive. High balance accuracy in F1 suggests it handled the imbalance well.
Extremely well. High F1 means good balance of precision, few false alarms, and recall, few missed risks. High balanced accuracy confirms it wasn't just getting the majority class right.
How did that compare to the baseline KELM and other methods?
Big improvement. The baseline KELM scored around 0.87 across metrics.
So Q-cherry tuning added almost 0.1 to the scores.
Roughly, yes. They also compared it to another hybrid, QPSO-KELM, using quantum particle swarm optimization instead of QoA. That scored 0.89.
Still significantly lower than Q-cherry-KELM's 0.96.
Right. And standard classifiers like random forest and SEC were also around the 0.86 or 0.87 mark. The QChOA-KELM approach really stood out.
Was this difference statistically significant, though? Or just noise in the cross-validation?
They addressed that. They ran statistical tests comparing QChOA-KELM against, I think, 29 other models. The improvement was statistically significant against 28 of them. For many comparisons, the p-value was less than 0.001. Even against the next best hybrid QPSO-KELM, the p-value was 0.0004.
So very unlikely that the QChOA action superiority was just due to chance.
Extremely unlikely. The results strongly suggest a real architectural advantage.
Okay, top-tier accuracy. But what about speed? All this complex optimization, quantum gates, does it take forever to run?
That's the other side of the coin, especially for finance, where prediction speed matters. Table 9 shows the runtime.
And the verdict?
QChOA-KELM was remarkably efficient. The average runtime reported was 0.09 seconds.
Less than a tenth of a second. For the whole optimization and prediction?
For the prediction phase after training and optimization, yes. That's very practical for real-time or near real-time risk systems.
How does that compare to the QPSO-KELM, the next best predictor?
QPSO-KELM took 0.12 seconds. So QChOA-KELM was actually 25% faster in execution time, as well as being more accurate.
Wow. So it hits that sweet spot. Best accuracy and highly competitive speed.
Exactly. That combination of top performance and efficiency is what makes it such a compelling result.
Okay, but let's talk practical deployment. In finance especially, you can't just drop in a black box. Even if it gets 0.96 accuracy, you need interpretability. How did they tackle the fact that KELM, like many powerful models, can be hard to understand?
Absolutely crucial point. For regulatory reasons and just for trust, you need to know why the model predicts high risk. They use the SHAP framework for this.
SHP? Shapley Additive Explanations.
That's the one. It comes from cooperative game theory and provides a mathematically solid way to attribute the model's prediction to each input feature.
So it tells you how much each feature pushed the prediction up or down.
Precisely. For a given prediction, the SHAP value for feature phi, (DIMX), tells you that feature's marginal contribution. And importantly, these SHAP values add up the sum of the SHAP values for all features equals the difference between the model's actual prediction and a baseline prediction, like the average prediction. It's called the additive property, shown in equation 11.
So it fully decomposes the prediction.
Yes, which is much more rigorous than just looking at feature importance scores, which might not tell you the direction of the effect or handle interactions well.
How do you get overall feature importance from SHAP then?
You typically take the average of the absolute SHAP values for each feature across all the data points, equation 12. This gives you a robust ranking of which features had the biggest impact overall on the model's output.
So you could see which specific financial ratios or market indicators were driving the risk predictions.
Exactly. That provides actionable insights. Financial analysts can check if the model is focusing on indicators that make sense from a domain perspective, which builds trust and helps meet regulatory needs.
Given the strong results and the SHAP interpretability, did the paper suggest other potential applications for QChOA-KELM in finance?
They did, because it handles nonlinearity well, works in high dimensions, and crucially, deals effectively with imbalanced data. They pointed towards areas like fraud detection and credit risk assessment.
Both often have rare positive cases, just like high-risk scenarios.
Exactly. The model's proven ability to handle that imbalance, demonstrated by the high balanced accuracy and F1 scores, makes it a promising candidate for those domains too.
Makes sense. But every system has limitations. What were the practical caveats or dependencies highlighted in the paper?
They pointed out three main ones. First, it's highly dependent on data quality.
Garbage in, garbage out.
Pretty much. You need access to clean, well-structured, temporally consistent financial data for this to work reliably.
Okay, fair enough. Second limitation.
It needs periodic retraining. Financial markets change, relationships shift. It's called concept drift. The model itself doesn't have a built-in mechanism to automatically adapt to these changes over time.
So you need a process to monitor performance and retrain it regularly on new data.
Correct. You need an active maintenance pipeline to prevent performance degradation as the market evolves.
And the third limitation.
It comes back to interpretability. While SHAP helps a lot, the underlying KELM model with its kernel mapping and the QChOA optimization process are still inherently complex. It remains something of a black box at its core.
So even with SHAP, for the most stringent regulatory environments, you might need additional layers or methods to fully satisfy transparency requirements.
That's the implication. Depending on the exact compliance needs, SHAP might be sufficient, or it might need to be supplemented.
Understood. Well, this has been a really thorough breakdown of QChOA-KELM. The way it integrates these different computational ideas, quantum-inspired updates, bio-inspired search, seems genuinely innovative.
It really does represent a successful synergy. It tackles the known limitations of simpler models and achieves that impressive 0.96 accuracy with remarkable efficiency, clocking in at just 0.09 seconds for prediction. It definitely sets a high benchmark.
The core contribution seems to be demonstrating this powerful hybrid computational framework as a superior basis for complex prediction tasks like risk management.
I agree. It shows the potential of combining these advanced optimization techniques.
Which leads nicely into a final thought for our listeners. We've seen how effectively QChOA blends quantum mechanics concepts with metaheuristics for financial prediction, showing proven convergence and efficiency.
So the provocative question is, where else could this specific QCOA approach make a difference? Thinking beyond finance, what other complex high-dimensional optimization problems, maybe in engineering, logistics, bioinformatics, material science, might be right for tackling with this kind of bioquantum hybrid optimization? The methodology seems robust and potentially broadly applicable.